So, I've been working on this problem since December 1999. So a long time ago. And I was sitting in Delhi at the meeting next to my dear friend Tony McMichael, who unfortunately died about 1.5 years ago from kidney disease. But I was sitting next to him because we were presenting at an IPCC meeting, Intergovernmental Panel on Climate Change, a report on the health impacts of climate change that we had both contributed to and written. And after Tony's presentation, I heard someone talk about climate change impact on agriculture. Then someone was talking about climate change impact on forestry. Then someone was talking about climate change impact on industry. And then I thought, this is crazy. None of these people even once mentioned the workers. It was like they had never heard the lecture that Andreas presented to us about the problems of heat and physical activity and the fact that such a large proportion of the metabolic rate and of the use of energy in the body actually goes just to waste heat and doesn't actually produce work. So that's what inspired me to start looking at this, because I had been a teacher for many years in occupational health for medical students and for nurses, etc. And I knew that heat is a very important occupational hazard. But of course it's also a hazard in the general environment, like Clea Katsuyanis talked about earlier. So it's a pity Clea isn't here, because actually I'm going to come to some of that analysis soon. So then we have, I think, a space scientist here. Someone's going to talk about space. And you have to realize that there is just one small place in the world where the thermal climate is important for human life. And this little planet where we are living. And it's very vulnerable. And we are on a track which is going to cause deep trouble. These are the 4 different RCPs. These are the pathways for future modeling of the climate change, and particularly of the GTC, as I call it, global temperature change, GTC. So if you see GTC on my slides, it means global temperature change. And that is what the meteorologists are particularly focusing on. And that's the part of the climate change modeling which is actually probably the most valid and likely to be relatively accurate, because the mechanism behind this has been known for 100 years, how the carbon dioxide concentration in the atmosphere creates this greenhouse effect, etc. I won't get into detail. But these 4 curves, the top one is what you call business as usual, BAU, and it's called RCP 8.5. And that's how the temperature will go up from now, or just before the year 2000, to 200. And in 2085, we will be just about 4 degrees increase. But this will keep going up to 7 degrees increase on average. And it's not the same all over the world. And it's quite likely that a country like Greece will be worse affected than this, even though, as you might have read recently, this analysis of the Canadian forest fires is making a link to climate change. And of course, up north in the Arctic area, the temperature is going up even faster than it does in Greece. In any case, the red curve is what's called the pathway 6.0, and that's very close to what was offered by countries in Paris. The green curve takes us to about 2 degrees, or a little bit more than 2 degrees increase in 2100. And the blue curve, the last one here, goes up to about 1.5 degrees and down again. So the politicians have said we really shouldn't be above 2 degrees. And then at the same meeting in Paris in December, 195 countries signed up for climate change policies and actions. We don't know if they're going to do it, but every country of this 195 actually signed this. And if you look at the promises for the countries, it will take us up to here. So it is about 2.7 degrees by the end of this century. And they said in the report, which they signed, really it shouldn't be higher than 2 degrees. So this is Paris at 2 degrees, and it's actually below what we call RCP 4.5. And then they said, ideally, it shouldn't even be higher than 1.5 degrees, which is down there at the same level as RCP 2.6. So I show you all this because it's a major, major problem for this world. How are we going to cope with it? You know? And I was fascinated when I was flying into Athens from London on Thursday to see all the wind power stations on top of the mountains on this island, which is just north of Athens. Ada, is it? Or, yeah. It was very impressive. But looking from the train, I saw very few electrical solar panels on people's roofs. There's a lot of water heating, you know, but very little electricity production. So if every roof in the world was covered in electrical solar panels, we'll solve the problem. It might happen, but probably not in my lifetime. Okay, so we have this problem, and I show these 4 curves again of the RCPs, and the Paris promise from the countries, the Paris 2 degrees maximum, the Paris 1.5 degree ultimum. I have a 4-year-old grandson in London. He was born about here, you know. He will be alive here. It's almost certain. So when the politicians and others are starting to think about policies for the future, you have to realize that these young children who are already around with us, they're going to be alive at the end of this century. Now his child will be about born here, and at that stage I probably won't be alive, extremely unlikely. So my grandchild's child will be alive in 2130. And the next child of that one will be alive in 2170. And the grandchild's grandchild up here. So if you think about it, it's actually part of your family. You usually don't know them further than the grandchild. But I have 2 grandchildren that are 25 years old. They haven't got children yet, but they might get some soon, you know. So I might meet the 3rd generation. I probably won't meet the 4th generation. Only Queen Elizabeth is the sort of person who would meet the 4th generation. But I show you this because it's very important, if you are a young scientist, to realize how extremely troublesome this is going to be. Not just for your life, but even more for your children's life and your grandchildren. You meet your grandchildren, you know. In the 2050s or 2060s, you will see your grandchildren. And they will be alive, you know, up here. So what happens in the world at that stage is very important. And that's one reason that this curve, business as usual, or doing nothing about the greenhouse gas emissions, is going to be terribly difficult because it keeps going up and doubles almost in the next century. Another thing which the... Are you there, Claire? No, she's gone for lunch. Another thing which is very important when you think about these curves of how the global temperature will change, etc., is that almost all of them, in fact all of them, are ignoring what we call the urban heat island effect. What does it mean? Yes, in the center of Athens, on a very hot sunny day, it is hotter than it is in the rural area around Athens, even at the same altitude, because you have mountains. You go up in the mountains, it will be cooler, you know. And this, of course, this is a graphic shown of a typical American city, but it's very important that you can talk about several degrees difference, and particularly at night, which is interesting. And of course, hot temperatures at night affect your sleep. But it also affects the afternoons, and it's very poorly researched, unfortunately. And it's the sort of research which is reasonably simple in a sense, and someone from this university, certainly a young person, could pick up this issue and say, I'm going to actually try to understand this urban heat island effect, and I'm going to demonstrate it in a country like Greece. I'll start with Trikala, then I go to Thessaloniki, then I go to Athens. And then you can see the difference on the islands, you go to Crete, etc. So it's a very important part of the heat problem. And why is that? Well, it is because it's where the people are which matters. Whereas the meteorologists, they are totally focused on the global average temperature, and they're thinking about the atmosphere. And they believe that this heat island effect is just a nuisance. It's a noise. It's a bias in their analysis. They don't want to deal with it at all. But in fact, for us, dealing with human health and the impact on physiology and on sports activities and on work, etc., this is extremely relevant. So this shows the type of analysis that my little team, I have a bunch of 7 volunteers working with me. Whenever I get a bit of money, you know, the money is shared between us and we use it for our research. This is the current situation of the heat levels, and we're using WBGT, which is a combination of temperature, humidity, wind speed, and radiation, but we calculate usually the indoor or in-shade values, indoor without air conditioning, in-shade values, which means the solar heat radiation is not part of it. We also assume that people are moving their arms and their legs and their body around at about 1 meter per second, which is, you know, probably typical for a job. Hi, Clea, welcome. So the calculations are a bit simplified, but it means that we can actually, in color schemes, show how hot it is. When it goes beyond 25 degrees on the WBGT scale, then you're starting to get problems for people who are working. And as you see, in West Africa, Northern Australia, large parts of Asia, and also large parts here, and even in the United States, already now, during the hottest month, it is actually so hot that people cannot physically keep going for a whole hour without taking breaks. And as Andreas showed earlier, you take a break maybe every 15 minutes. Yes, of course the body cools down, etc. But some people are in jobs when they can't do that for a variety of reasons. So it's a difficult problem for them. In 2085, this is how it's going to look. And you can see how the red areas are spreading north in the United States, maybe even up to Pittsburgh. Our friends from Pittsburgh have left. I was hoping they're going to look at this. But a large part of the United States are going to be so hot that at least the hottest month, not the whole year, but the hottest month is going to be trouble. And of course, here you can see in 2200. And this is RCP 8.5. So it shows what is likely to happen if you do nothing about climate change, or if the politicians and the communities do nothing. And it's also important to remember, where are the people in the world? This is for every half-degree latitude band around the world, the number of people. And here is 100 million. So there is one latitude band here, half-degree, which includes Shanghai and New Delhi and some other big cities, where there's more than 100 million in one thin band around the world. But it also shows you that between 40, plus 40 to minus 40, which is sort of the range of the tropical and the subtropical areas, that's where the people live, you know. They don't live up here in the Arctic. And it's true that the climate change in terms of temperature increase already is worse, and it will be even worse up in the Arctic area, and the ice will melt, and this will cause other troubles. But in terms of the heat problems, this is where they are. And as an epidemiologist, I always think of, where are the people? You know? and this is on a longitude basis. Okay, so there are lots of climate-related health effects, and I won't go through all this in detail, of course. I worked for 12 years at WHO in the 1980s and 90s, and we developed this so-called deep sea framework, where you have the driving forces behind some environmental hazard. You have the pressures on the environment, how it's going to change, what is causing the change. You have the actual measurement of the environment, and then you have the human exposures, which may not be the same as the actual levels in the environment, because, for instance, with heat, if it's extremely common for people to have air conditioning, both in their apartment and in their office and in their car and in their shopping center and wherever else they go. I mean, you think about Dubai, Singapore, etc. Then, of course, you won't have mortality caused by heat levels in those sort of cities, or at least not as much increase as was shown by Claire previously. So the human exposure is not necessarily the same as this. And finally, you have specific effects on health, and then one can classify these into different ill health categories. And we can find examples of child health, health of the elderly, women's health, occupational health, communicable diseases, non-communicable diseases, mental health, injuries, you name it. All of these things, in principle, can be included in what might happen due to climate change in a specific community. So just to show you an example, if we say, oh, let's start at the local climate change, and then to see how does it change heat exposure. It causes heat exhaustion, heat stroke, and it's part of our program that I'm involved in called hot HAPS, and people even die, of course, as Clea mentioned. And this is one of the aspects of occupational health that I'm talking about today primarily. So we can go through these different health problems that may occur related to climate change and find that working people in many of these situations are the vulnerable ones. And it was interesting when Clea mentioned that in northern Africa, the cities which were part in one of her studies, actually the younger people were more affected than they were in Europe. And my immediate thinking was, is it because they're actually working and they don't stop working when they should stop working? You know, in the United States, 40 agricultural workers, young people in their 20s and 30s, die each year working on the farm field, and they don't stop when they should stop because they haven't been to Andreas' lecture about, you know, physiology and protecting themselves, and they don't drink enough water. You know, they just pass out and then they die. It's very difficult. If you get so heated that your body temperature is up at 41 degrees or something like that, you pass out, you faint, taken to hospital, and in that case, it's very difficult in many cases to revive the people. And of course, they've had big problems in Mecca during the Ramadan, you know, people when it's in the very hot part of the year. And there's lots of research on that. So it's interesting that the fact that people actually dying from heat is not just an issue for the general public, but also very much for workers. So we have extreme weather events, working people, where we have the firefighters, we heard about that today. We have, of course, the general public. If you have a terrible storm in a country like the Philippines, there might be thousands of people affected by it, similar to an earthquake, and their houses are washed down the rivers, etc. We have occupational heat stress, and I'll come back in more detail to that, but in a sense it's the most easy to calculate. It's the most obvious thing. We have kidney disease due to daily dehydration. I mentioned it earlier today. 20,000 young people have died, agricultural workers in Central America, and it seems like another 20,000 have died in Sri Lanka in agricultural work. And it's very likely that dehydration on a daily basis is a factor in that. But research is still going on, and prevention is pretty obvious. Make sure they get water, make sure they get minerals to drink, you know, because these guys are working 8 hours a day. They're not just in a laboratory for a few hours. Vector-borne diseases, well, you know, if it gets so hot that you can't work during the middle of the day, if you're a farmer in India or in Bangladesh or somewhere like that, or even in Greece maybe, then you end up working more early in the morning, before sunrise and during sun, and also late in the afternoon at sunset. And in a country with mosquitoes spreading malaria, that's when the mosquitoes like biting you. In the middle of the hot day, they're not so into biting as they are in the morning and the evening. So it may very well increase the risk of any of those vector-borne diseases. You have ecological change diseases. Of course, in China, for instance, they have done research on the spread of certain diseases, again related to infections that are particularly affecting working people. And I won't go into detail, but we can talk about that later. You have other infectious diseases spread via dirty water, etc. You have a lack of food, which of course is a big problem for babies, and that's what WHO calculates in their mortality analysis. But it must also affect working people. If you haven't got enough food, you know, you can't work as hard as if you're well nutritioned. So that's a part of what might happen to working people. You have mental health problems and finally increased chemical exposures. If you're working in a factory where you're making shoes, for instance, and I'll show you a picture, and you're using glues, and the temperature is normally 30 degrees, well, the glues are evaporating from your bench there at a particular rate. If you increase the temperature to 35 degrees or even 40 degrees, then of course the evaporation goes much faster. So in the air around you, you have a higher concentration of this particular solvent that is in the glue. You inhale it, and there you go. You get poisoning. All right. Now, Clea, this is for you. Now, these are the original data from the French heat wave in 2003. And it's the number of people, the additional number of people dying in France during the 2-week period. There was 5,200 men and 9,500 women, about 15,000 together that died during these 2 weeks. And this is on top of the normal level. So they took the average of the 3 previous years, and you subtracted that from this particular year, 2003. So do you find anything interesting in here? Die Hard. Is that on your T-shirt?
No. It's a mark.
Die something. Can you see something interesting here with men and women? In the numbers?
Women are more vulnerable.
Sorry?
Women are more vulnerable.
Yeah. If you look down here, there are more women down here, yes. Can you see the table, Clea?
Yes, I can, but women are older when you adjust for age.
Yeah, that's right. Women are older. And of course, because of that, and because of the numbers involved, then the epidemiologist in France, this was published only two months after that August heat wave, the epidemiologist in France focused on this particular group. So there was overall elderly women who were the victims of this heat wave. So that's extremely important to know. And because of that, a lot of research on heat mortality has just focused on this people over age 65. They thought, well, let's just count numbers over age 65. But is there anything else you can see here? Yeah?
There is an earlier onset on men concerning the...
In younger ages is the opposite.
Yeah. That's a way to look at it. Look at these numbers here. And these numbers. All right? In every age group below 70, there were more men dying than women. In fact, The youngest women, up to age 40, they had less deaths than the years before. The women are clever, you know, they realize it's a heat wave, I better take action here and protect myself. Are you gone, Clea? What a pity. Anyway, so when I saw this table, I thought about that group. I thought, that's amazing. And why is it that men are more common in terms of the number of people dying extra? It wasn't proving that it was caused by the heat wave, but it was happening during the heat wave. And then the first thinking of me, because I'm focused on the occupational health thing, is it because they were working and they didn't stop when they should have stopped? And therefore their body got overheated and they got so hot that they passed out, taken to hospital, and they died, because in many of these cases you cannot treat them or cannot get them back. And you know, no research has ever been done on this. I met some of the French meteorologists involved, and they checked with all their colleagues this years ago. Oh no, 2009 it was actually. No research has been done, and I've been hoping to find a young person with medical training and fluency in French to go over to Paris or to wherever these data systems are, sit down and look through all these records. They probably still exist, you know. You can go and see what were these people doing when they got so sick that they ended up in dying. The elderly people, most of them, or many of them, died at home alone, and they were found maybe a day or so afterwards. But these young people, it's extremely unlikely that they would sit at home alone and die, you know. They'll take action. And of course there are some mentally ill people in this young group, you know, who didn't take action. But it's a fascinating potential research topic that has never been looked at. And if Claire has a lot of data on younger age groups in Greece, of course you may be able to do the same kind of analysis, trying to see what were these young people doing before they died. And some of them were taken to hospital, so that in the hospital record there might be a story written in Greek about what they were doing. All right. So that's just the link to the mortality analysis that is being done. And I think it's unfortunate in terms of research that a lot of this mortality focus is driven by the fact that data is available. So the statistician can calculate, you know, the temperature data is easy to get, and they have mortality data, and they crunch numbers, and they have fancy, beautiful fitting statistical curves, etc. But in fact, it may be just as important to do studies of small group of people and actually following up what happened to these people. And my own thesis, I had people in the Swedish factory, 200 workers. I had Japanese farmers, 60 workers and 60 farmers in one place, and about 50 in another place. And these small-scale studies, if they're very precise and looking at a particular issue, can be extremely important. All right. So we have lots of vulnerable groups among the workers, tropical and subtropical countries, I already mentioned that. Those who have to work continuously at high physical intensity. And for instance, in a car factory in India that I visited, where in the hot part of the year, it's always hot, but the hottest part of the year, it's 42 degrees inside the factory. You can imagine. And it's like Charlie Chaplin, you know. And these guys cannot keep working. So they work 5 minutes in the hot part of the year. And then someone else comes and works 5 minutes like that. Means they have to pay 2 salaries due to the heat. Whereas in the cool part of the year, when it's only 35 degrees or 30 degrees inside the factory, the guys can keep going, you know, for an hour and then just have 5 minutes break or whatever. So that kind of continuous work situation is very difficult. We have agricultural workers, of course, these people with the kidney disease. In Nicaragua, they are cutting sugar by hand. The sugar ends up here in Greece and in Europe, at your table, you know, and they get paid almost nothing, of course, for doing this work. And they have a target every day. 2 tons of sugar has to be cut, for instance, which means that if they start at 7 o'clock in the morning, they finish at maybe noon, and if it's a hot day, they have to work another hour. So they are particularly affected, many agricultural workers. Construction workers in the south of India again. I met the manager of a company and asked him about the heat problems. He said, oh, yeah, no problems, you know. In the cool part of the year, the workers have a 1-hour lunch break. Yeah. In the hot part of the year, they have a 5-hour lunch break. Ha, 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 ha. So basically, they work 10 hours a day, but they have to work 6 hours before the lunch break, 4 hours after lying under a tree sleeping. So the construction workers are already very much affected. And if you go to India in the hot part of the year, you'll see it, you know. They're lying somewhere in the shade sleeping in the afternoons because it's impossible to work. Then we have the emergency workers. And there again, it's quite interesting. When it gets very hot, they also get very tired and they have protective clothing on, etc. And there's research done from a group in Darwin, Australia, where they have actually quantified this and they've done experiments and they can show that the emergency workers are slowed down. What does it mean? It means if you have a terrible catastrophe in the Philippines, they're sending in people from Australia and they say, I need 100 firefighters or I need 100, you know, reconstruction workers. And in the Philippines, it's so hot that they actually can't work for more than half an hour and then they have to take a break. That means that you need twice as many workers as you would if it was cooler. In the Ebola epidemic, these people were working in plastic bags. After 20 minutes or 30 minutes, I mean, the plastic bags they were in, they were totally full of water, almost, you know. Full of sweat, terrible, because the sweat doesn't evaporate. You're sweating like a pig, but the sweat doesn't evaporate. So you have to take this off. And of course, the worst problem for these health workers in the Ebola epidemic is that the time when they take this clothing off is the most dangerous time for them to also get in contact with these microbes that cause Ebola. We wrote a paper that which was actually published by Kuklane et al. Last year. And it's quite interesting, you know, that the climate change making it hotter and hotter will create larger and larger needs for emergency workers because they can't cope. We have migrant workers, and of course they are usually underprivileged, etc. I won't get into details. Workers in factories or workshops without efficient cooling systems. And then workers in slum workshops, of course. I mean, you have just a metal roof over your head, which actually heats you. All right, sorry, I'm talking too long. Are you okay? You don't mind? All right, so here are just some pictures. These are construction workers in India, the people who have a 4-hour lunch break. This is early in the morning. This is a shoe factory in Vietnam, 2,900 young women. And I was there to look at chemical problems, and the manager said, oh, we have no problems. But he and the managers in 6 other factories all said, it gets very hot in the summer. That's why I asked him. That's interesting. What's happening in the summer? Come back to that. This is the Nicaraguan sugarcane harvesting people. And you can go in with a machine from Australia and do the work in half the time or even less. But then 5,000 people get unemployed, you know. So it's very difficult in those situations. Let me just show you this first. This is inside this factory. And these women, they have the same target for their production every day, regardless of the temperature or the heat, which means that in the summer, because they cannot cope going at the same speed, they work 2 hours longer. They get paid the same, but they at the work for 12 hours instead of the normal 10 hours. You know. All right, so there are only 2 studies that I have ever seen that relate the heat levels, in this case the WBGT which when it's above 26, it supposedly starts affecting people who work hard. And the increase here is similar in scale to temperature increase, because the temperature is of course the most important part of this, even though humidity also has a very important role, and I'll come back to that. This shows the blue dots here, the first hour of the working day. Each dot is 10 to 15 workers, and as the heat during the first hour is higher, then the productivity goes down. This is the number of rice bundles that these workers were collecting per hour. And because they got paid by the number of rice bundles, there was actually data on this. And it could be used to show the what we call exposure-response relationship for the reduction of productivity. And the red dots here, that's the 5th hour of the day, so that's just before lunch. And as you see, it's about 5 bundles less, and because they get tired. So in the 5th hour, they can't do as much per hour as they do in the 1st hour. And it's shocking that this study by an Indian professor, and I was involved in it, and studies from the 1960s in a South African gold mine is the only quantitative evidence available on the effect of heat on productivity in workplaces. So if anyone in this group or in this university is interested in this topic, and you can work out a way, even on a small scale, to actually quantify these sort of heat effects around Trikala, it would be marvelous. Because we need more data of this type, you know. I'm trying to get data from factories in Cambodia, actually. And they are factories producing almost all of their material for the Swedish global corporation H&M. And I was there visiting last week. And inside this factory with, remember this? 5,200 young women. Can you imagine a factory with 5,200 people sewing stuff for that T-shirt that you have on, you know? That's what they're doing all day. And it was 31 degrees WBGT inside. They allowed me to measure, and in fact, it may be that we can make additional studies of this. And I have some of these with me, so if you're interested, we can talk about it later. This is a temperature humidity data logger. You put it in your computer, like that. You program it to measure temperature and humidity at 1 hour intervals or 5 minute intervals or whatever you like. And then you just put it somewhere. You can, this, if you want, worry about the lecture room, put it here, put tape around it, and you leave it there for 3 months. All right? Then you come back, put it in your computer, and you have the hourly data for 3 months. And you can calculate from temperature and humidity, at least approximately, the various heat stress indices that combine temperature and humidity. All right, so here we used WBGT, which combines the two. And by the way, I don't disagree with Clea that humidity doesn't come out in the statistical calculations. But a problem is, of course, if you do studies in Southern Europe and you have daily data, the humidity doesn't always change that fast. So you have to compare a study with very low humidity or a city with very low humidity with a city with very high humidity at the same temperature to see what role humidity plays. And in addition, it is mainly a problem when you come to high temperatures. So you've got to be up there by 25, 30, 35, 40 degrees, you know. I can see clear-eyed nodding. But it means that actually that kind of statistical analysis is still required if you're going to understand this. Right. So there you go. The other thing, chemicals I mentioned. So this woman has a piece of cloth here, not very effective when it comes to organic solvents that she's inhaling from this gluing that she's doing of parts of the shoe, you know. And no research has ever been done on this. So if any one of you are interested in toxicology, it's a marvelous topic, you know, to see how does it change. And you can start with the laboratory work, changing the temperature and having people doing something where there are solvents involved. And you have all the people painting, you have all the people doing gluing, you have a lot of other industrial activities where solvents are very important. All right, so this is the world again. And here my little team has calculated with one of the IPCC models for 1995 the percentage of annual hours in the daylight that are lost because it's too hot. And you can see that according to this calculation, that in Greece there is no such change, whereas in Pakistan, poor buggers, they're terrible. They're 5 to 15, even more than 15% of the annual number of hours are lost because it's too hot. That is no surprise to us. You know, there are places in the world where it's so hot you can't actually work all the year, you know. So that's 1995, and it's at quite active, intensive work level. And this is 2085, same model, and this is business as usual, so the global temperature change 4 degrees. Look at the poor guys in, in the Amazon forest, you know. It's terrible. This is the hottest, this is the annual daylight rise, so it's the whole year. We add it up for all the months. And you can also see northern India is going to lose up to 25, maybe 30%. And Cambodia is here, also will have serious problems with this. Now, in a report that came out 2 weeks ago from the UNDP, and I can send it, I don't know if I sent it to you, Andreas, but I'm happy to share all this stuff, including all the PowerPoints with you. We calculated for 2085, and it's the change in the annual daylight work hours lost. So it's how many percent of the work hours are you losing? And of course, here we have these columns. This is 1.5 change of GTC, 2.4, which is close to 2.0 for the aim, 2.7, which is what countries have offered. This is business as usual. So in the case of Greece, by 2085, you will only lose 1% of your daylight working hours. But you know, how many hours are there? 365 we calculate every day, times 12, that's 36,000, that's 40,000. So 1% is about 40 hours. It's not much. But if you're looking at India, 14%. So that's 14 times more than Greece, you know. And the worst place happens to be Cambodia that we have calculated for. And even these Pacific islands, that Kiribati, which of course will have other problems because it's sinking under the sea. But because the heat goes up, they're going to lose 18 or 19%. Ethiopia is not as bad as Ghana. What do you think is the reason? Can anyone imagine?
I guess because it's close to water.
No. What's the big factor I haven't talked about?
They work at night?
No. What is it? What is it? It's a very important part of this whole global analysis. It's the altitude. Most people in Ethiopia are up there at about 2,000 meters, you know. That's where Addis Ababa is. It's a bit like Mexico City, which is also almost at 2,000 or 1,500 meters. So it's naturally cooler the higher you go. And in theory, you know, people down at the coast will have to move up to the mountains. But I just mentioned that to show you that there are interesting features of these types of calculations that come out when you actually do the calculations in detail. And by the way, this is based on 67,000 so-called grid cells, half by half degree grid cells. So the whole thing will cost a lot of money, and I won't go through this in detail, but the only calculation so far of the global cost of the heat-affected loss of labor productivity is that by 2030 already it will be $2.4 trillion. It's a lot of money. In Greece, you know a lot about money, of course, but this is enormous. And interestingly, it's only 1.5% of the global GDP, or the total money, you know, is turning over in the world. So in that sense, it's not a major, but if we just manage to reduce this by 10%, it's 240 billion, and you can use that money in a more intelligent way. And of course, the worst affected countries are those countries those developing countries that either have low emissions or high emissions. So China is here, and India is part of that. You know. But India's emissions are going up. All right. Just to finish off, we have 2 tools that you might be interested in testing out if you want to explore this thing. One of them is called HotTabSoft. It's got daily data from 18,500 weather stations. And Clea mentioned the problem of getting data from some of these cities. Well, the data are freely available, and it's just difficult for you to download all these data from the American website where they sit. Now we have made the whole thing very user-friendly. And the actual software doesn't only take more than a few hundred kilobytes, and the database is 4 gigabytes. And it's now set up so you can actually access the data over the internet. It's got 7 climate variables. It's got various outputs here, and I'm not going to show it to you in detail. But again, it's intended to be a useful tool for researchers, and if you use it, you just have to say HotTabSoft, you know. You don't have to ask anyone for permission. We can compare the same location with the grid cell data, etc. And we're working on health risk functions. And this is just an example for Istanbul, for the airport. This is how the annual WBGT, we calculate that as well, has gone up by 2 degrees for the last 30 years. And it doesn't sound like much, 2 degrees, who cares? But what this software also does is to look at the threshold analysis. So actually, in 1980, there were only about 7 days that WBGT was higher than 25 degrees. And now it's more than 30 days. So they have got 3 weeks longer of super hot days that affect working people. And if this curve keeps going, after another 30 years, they're going to have terrible problems in that part of the world. And of course, it drives air conditioning and things like that. You know, we know that. So now the other tool, which I actually can show you, is the climatechip.org. So write down this if you're interested. It's again very user-friendly. You just write climate chip into Google. First thing you see is this one. And it's called Climate Change, Health, Impact and Prevention. It's not finished yet. But what we have is a system to look at individual grid cells. And this again shows for Istanbul, the hottest month, how it has gone up from 1980 to 2011, and this is actually based on real data. This is not some fancy model that comes from, say, some meteorologist thinking up what to do. They actually used the original data, and this is one of the worst places in the world where in the hottest month, August, the temperature, this is the max temperature, goes up almost 1 degree per decade. 1 degree per decade. And this part of Greece is also one of those places where it goes up quite a lot. So let me see. I'm almost at the end with this. Yeah, can we switch over?
Yes.
Is it okay?
Sure.
So I have it here. What I actually will do, I will finish off my PowerPoints because I realize we're running out of time. But we have it sitting there, so any one of you want to see how this works, we can do it after I'm finished, because I realize some of you have to go to other things, you know. Is that okay? Then we go back again. Yeah, so, oops. There you go. So I will show you this in the climate chip, but it's very self-explanatory. You go in there, you look at your area, click on it, and then it says today and tomorrow. You click on today, and the whole global system knows where your computer is sitting. So it will show you the grid cell around Trikala. And then you get the maximum temperature trend for the last 30 years, etc., etc. All right. So what I hope through this visit, of course, is to inspire some young people to work with Andreas and with me and with others to boost this research on this topic over the next 5 years when we have this heat shield project, which Andreas is one of the important person in. And there is this issue of current climate and current heat exposures and how it affects the occupational health and productivity. We don't have to wait, 30 years to see what's going to happen. Why not? Well, the heat level in Phnom Penh in Cambodia is now what Athens will be 70 years from now. Okay? It's not the same, exact the same annual pattern. But you can look in climate chip and you can see that the current situation in Phnom Penh is like where Athens will be in 2070 or 2080 or something like that. Which means that we can actually do studies in Phnom Penh or in other highly populated places in these very hot places, and we can learn about not just the physiology, of course, but the practical occupational health impacts and the mortality impacts on the local people. Very, very few studies have been done in these countries. And it's a real pity because it means that a lot of the analysis of climate change impact is sort of starting from Europe or North America and how the data in those countries show what's going on. So we have that. And we have links to prevention and adaptation methods. Can people actually, are they going to be able to cope? And what's the limit to the heat exposures that goes beyond what they can cope with? And then we add to this the future climate. And again, as I said, you can look at the future. The future is already there. In Chennai in the south of India, in Phnom Penh, in Dhaka, you name a favorite place of yours in the tropical world, you can immediately in climate chip see what is the current situation, what is the future situation, according to 5 different IPCC models. And of course, we have the issue of population exposed. Well, we have in our data set the populations for every grid cell, 67,000 around the world, by age group, which means if you're particularly interested in elderly or children, you can actually use our data set to calculate that. That's not on the website yet, but we're happy to share this with any research team because it was all intended to be public good. So there are a number of things left to study, but I think I'm going to stop. I won't go through it in detail. Better understanding of medical mechanisms. We have issues like the heat-sensitive enzymes. Very little research relating to climate change. We have risks between different age, gender, occupation groups. We have evidence about psychological or mental health, impact of heat on children's learning. Millions of children are sitting in schoolrooms where it is 35 to 40 degrees, They have no air conditioning. In fact, in Africa, they have no electricity. And they go to school in those conditions. Terrible it is. We have need for improved quantification of the links between heat and productivity, the economic impacts, etc., etc. So I'll give a copy of this to Andreas, and he can share it with any one of you. So I think I'll stop there. And it's an underestimated future risk. We need lots of research, and I'll be very happy to work with you here. And if you want to write to me, that's my email. Thank you.